Welcome to RF transceiver design course. We are discussing about mixer design, and in last class we have seen passive mixer, M phase passive mixer, and we have concluded that if it is 4 phase or 8 phase, the gain is around 0.97, that is equivalent to the 1. So, mostly we will go for M is equal to 4. Now, we will discuss more about the passive mixer. So, if we want to understand the operation of passive mixer, here the important in this figure, the important part of the passive mixer is this is a TIA, trans impedance amplifier. So, if you represent the trans impedance amplifier as a ZBB, that is a impedance of the baseband, and because it is considered a differential, it is a 2 into ZBB. And here this is a current, that is RF current is applied to the passive mixer. So, here each TIA has a single ended input impedance denoted by ZBB, and the effective LO signal, that we are already discussing multiple times, that by making a more phase non overlapping clocks, we are trying to mimic the signal as a sinusoidal wave, means LO signal instead of a square wave. So, here if effective LO signal, which is denoted by S1t, S2t for LO1, LO2, LO3 respectively, and if it is toggle between 0 and 1, and if we represent the Fourier series representation of effective LO signals, we can write S1t, which is a sigma n minus infinity to infinity n e raised to j n omega LO t. S2t, because there is a this is a non overlapping, it is shifted by pi by 2. So, e raised to minus j n pi by 2 e raised to j n omega LO t. So, the difference between this LO1 and LO2 is a 180 degree phase shift. Now, there is a S3, which is a 90 degree. So, we can write a n. So, this is a n e raised to minus j n pi e raised to j n omega LO t, and S4t, which is equal to e raised to n minus infinity to infinity a n. Again, this is shifted e raised to j n pi by 2. So, this is a plus pi by 2 and this is a minus pi by 2 e raised to j n omega LO t. Here a n can be written as a e raised to minus j n pi by 4 by 4, where and it is a sinc function n by 4. So, we can represent the different S1 to S4 switch Fourier representation. Now, what is we are trying to see that at input side how the baseband impedance looks like. So, since a given switch is on only 1/4 of cycle, because here this in entire 4 quarters. So, if we divide 0 to t period in the 4, because we are applying a 4 LO non overlapping LO. So, during this entire quarter cycle, this only one switch will be on, that is LO1, and then LO2 and then LO3 and LO4. So, same thing is written 1/4 of cycle. For the corresponding branch, the I switch toggled by LO1, and we can write IBB I plus, which is S1t into IRFT, that is S1t multiplied by IRFT. So, this baseband current in turn creates a voltage across the input of a TIA, because this current is then pass through the impedance, because it is a TIA trans impedance amplifier, and this baseband voltage is only transparent to the RF input when S1 is 1, and thus effectively multiplied by S1 when monitoring the RF voltage. Now, if we consider all the 4 branches and switch resistance, we can write VBB I plus, which is equal to S1T IRF into ZBB T. Now, VRFT we can write R switch into IRF. If we are interested to see what is a VRF at this place, that R switch into RF plus the combination of this all. So, SKT where K is equal to 1 to 4, which is for each cycle LO1, LO2, LO3 and LO4, SKT into VBVI plus S1T IRF into ZBBT. So, this is a VRFT. This again this can be written in this form, that is a N and M, that is AN AM IRF omega minus N plus M omega LO ZBB omega minus omega LO. So, what it represent that at the input side, if we consider the impedance. So, if we want to represent, if this impedance which is if you try to see at this point at VRF, then it will be nothing but the up converted version of the at LO frequency omega LO. So, this V, the RF voltage we can write in terms of current and switch resistance, and here it is multiplied with the Z baseband resistance omega minus N omega LO. If the RF current is a sinusoidal at frequency of omega LO plus omega M, if RF current is a sinusoidal which is input, then the RF voltage has its main component. So, we will get only one component, which is omega LO plus omega M, and receiver provides some modest filtering. So, we will have N plus M, which is equal to 0. So, at this point, because we are interested for the signal where if omega LO plus omega M, which is the RF voltage. So, at that point N plus M is equal to 0, and we will get VRF, which is a, and here we are only consider the omega minus N omega L and the signal which is at the input side, which omega LO plus omega M. So, the impedance seen at the RF input nodes as VRF omega, which is equal to R switch IRF omega plus 4 times e raised to n minus infinity to infinity a n square IRF omega into ZBB omega minus N omega L. So, if you take the, if you consider that this is a switch resistance and this is a impedance that you are seeing at the input side of the passive mixer. So, this is what happens, that this is a ZBB, the impedance with respect to the frequency at the baseband. So, this is a representation of the TIA. So, this is a representation of this TIA. Now, that will be up converted at this point, and that is at LO frequency FLO and minus FLO. So, what this indicates that TIA input impedance is appearing at RF and at around the LO frequency and its harmonics. So, it is also appearing at its harmonic, but the amplitude is high at a FLO. So, this is how we can also use this passive mixer, different phase passive mixer as a filter also, and that is why if we write a input impedance Z in omega at vicinity of omega LO, that is R switch plus 2 by pi square ZBB omega plus omega LO and ZBB omega minus omega LO. So, the baseband impedance is transformed to the input around omega LO, and accordingly if the baseband impedance is a low pass, the corresponding RF input sees a band pass impedance whose center frequency is precisely set by the LO. So, if you have a baseband filter and that baseband filter which is at low frequency, you can easily up convert by using a passive mixer. At the input side it looks like that your baseband is up converted to the omega LO, and this property may be utilized to create a low noise narrowband filter, and it is often or widely represented as a N path filters. So, N path filters are widely used. The advantage of N path filter is whatever low pass configuration that is at baseband, it will be up converted at the input side, and it will help to realize the high Q filters by using the switch configuration and the baseband filter. So, what happens that at RF frequency this Q, because Q is inversely proportional to the bandwidth, and if we want to realize the filter with inductor or any other active components, it will consume a high power, or if inductor requirement of the Q is very high. That is why this approach will help to realize a filter at high frequencies. And another advantage of this kind of filter, because this is a vicinity of omega LO. So, if you change the LO frequency, and your filter also will be tuned at that frequency. So, it will also add the reconfigurability in the filtering. So, it can be replaced, means it can be one of the replacement of the SAW filter, which is a widely used in the RF design, and we can tune it and use it that filter as a software for the software defined radio. You can read more about the N path filters in the literatures and in the papers available. Now, we will see the noise consideration in passive mixers. There is a minimal noise with the non overlapping LO signals, and passive mixer with non overlapping LO signals have a very less noise contribution, and switches in the triode region with 0 bias have a negligible 1 by f noise. So, that will reduce the 1 by f flicker noise, and well designed passive mixer typically exhibit a negligible 1 by f noise. So, we can get rid of the 1 by f noise which is more in the active mixer, that can be reduced in the passive mixer. And for thermal noise contribution, at any given time only one switch is active, and its resistance and noise are in series with the current from the GM cell. So, that switch resistance needs to be considered, and for that noise voltage spectral density is a 4 kT R into switch. So, R switch is a switch resistance. So, the current noise spectral density, which is 4 kT R switch by the total impedance that we will see, because we are using the at the load there is a trans impedance amplifier and ZL square, and if you have a GM cell is ideal, and at the input we have a transconductance amplifier. So, if GM cell is ideal, then ZL is a infinity and switches contribute almost no noise. So, this is one of the advantage of using a passive mixer, where we can have a negligible 1 by f noise by making the switch in the triode region, and also that because of the GM cell at the input side, that is conductance amplifier. If you have a ZL which is infinity, your resistance means your noise contribution is less. So, in this case GM cell at the input side is important, because we all know that the first component will affect the noise contribution in entire receiver chain. So, impact of switch mismatch, if there is a switch mismatch. Now, mismatches between the switches can lead to leakage of flicker noise of the GM stage. So, this is a GM stage and stage to the output. So, that will be leakage, and the leakage gain is 2 times of V offset by S n to T. We already have derived how this S cross T came, and where offset is the input required offset voltage, and S cross T is a normalized slope of LO signal. And high pass filtering such as a blocking capacitor can suppress this noise. So, this noise can be suppressed by adding a blocking capacitor of to that we are using for the DC blocking, and that will help to reduce this noise, which is generated by the GM stage. So, this is a representation of the GM stage, where this is a load and this is a current IRF, and this is a noise current Vn by ZL, and this is a 4 kTr switch that we have already considered. So, the using of blocking capacitor will help us to reduce the noise. Now, linearity in current mode passive mixer, the superior linearity compared to the active mixer. This is a passive mixer, and passive mixer has always a better linearity compared to the active mixer, and here we are using in current domain. So, what is happening that this is a blocker here, and this is a desired signal. When there is a GM cell, after the GM cell we have already seen the importance of using a input impedance. So, that Z in input impedance at RF frequency is R switch plus 2 by pi square ZBB, and this input impedance is 0 for means it will only pass, it will be like a filter, it will only pass the only pass the band which is the desired at f LO frequency, and other frequency component will be rejected, and we do not need additional filter here. This will filter out the other frequency component other than the omega LO frequency, and then we are going to down convert to the Z baseband at the baseband by using a TIA. So, in this current mode passive mixer, the design of TIA is important. How well you have designed the TIA, transimpedance amplifier, which is going to reject, means you can design a TIA which has a better rejection at the frequency band and stop band and pass band. If we realize by using a ZBB, then we can have a better linearity, it can easily block the blockers. So, this figure demonstrates demonstrate the scenario of small desired signal with a large blocker. It can easily filter out the blockers. So, for in terms of linearity, this configuration current mode passive mixer is widely used, and it can be used for a blocker resilient receiver design. And impedance transformation, as I discussed, and a small input impedance. So, if the TIA presents a very small input impedance to the switches and switch resistance is a low, the GM cell sees a small impedance as its output. So, this ensures a small swing at the GM cell output, and a large capacitance at the TIA input creates a band pass filter that suppress the blocker. So, same thing here, the configuration of the uh, ZBB means design of a TIA in combination with the capacitor will help to make the response like a band pass filter, and this down conversion shift the signal to DC while the blocker remain at a higher frequency. So, this low pass filtering easily suppress the blocker, and it ensures the filtering does not affect the desired signal, is typically feasible due to the large ratio of blocker offset to the signal bandwidth, and it is a 5 or 10 times. So, this phenomena of up conversion of the baseband impedance will help us to reject the unwanted interference blockers or jammers. Trade-offs and design consideration. Larger switch size leads to a more blocker suppression if we have a switch size which is a large. However, mixer buffer power consumption is increased. So, designing a TIA is a critical, particularly for maintaining a low input impedance, and blocker tolerance is substantially enhanced compared to the traditional voltage mode receiver. So, this while designing the TIA, it should be ensured that the input impedance is a low, and which will be up converted at the input of the passive mixer. Now, if we discuss about the second order distortion in passive mixer exhibits second order distortion mechanism similar to active mixer. So, this mechanism includes a direct leakage of a second order component due to mismatch among the mixer switches. That leakage gain can be given by 2 V offset by S into T. There RF to LO coupling in the down conversion mixer leading to IIP2, which is equal to 2 S into T divided by pi alpha, that we already have discussed, where alpha is the leakage gain. So, if we can reduce the leakage alpha, we can improve the IIP2. Non-linearity of the mixer switch is caused by a beta and threshold voltage mismatches. So, this if we want to reduce the linearity, if we want to reduce the non-linearity or improve the linearity performance, then what we need to do is the leakage should be avoided. In order to remove the reduce the leakage, the overlapping, if we can reduce overlapping cycles, then that will help us to reduce the second order non-linearities. So, attenuation of IM2 component, series capacitors between the LNA and RF GM cell and the switches attenuate the second order components generated inside the LNA and preventing their contribution to receiver IP2. Second order IM2 sources may contribute to IP2 by modulating the resistance of mixer switches and affecting their on off timing. So, that is why this series capacitor is important in if we want to improve the IIP2 of the passive mixer. Modulation of switches resistance versus timing. So, modulating the resistance of switches has a more significant impact on IM2 products than modulating the switching time. So, that resistance is that because this resistance is changing as the LO because at one point of time we are switching it on and it is a off for other 3 cycle. So, passive mixer switches are clocked by rail to rail signal with a fast rise and fall times, minimizing the timing related distortion. So, that should be ensured, and the conclusion is a properly designed passive mixer with 25 percentage clocking is expected to have a reasonable small contribution to IP2. So, the leakage is important. Another point, if we can introduce the differential nature, if we add a balun at the input and add a differential configuration of each, so it will also reduce the IIP2. So, this is how we can improve the second order nonlinearity in the passive mixer. So, TIA design choice. So, how we can because TIA is important for designing this passive mixers, current mode passive mixer. So, what is the drawback of simple TIA configuration? A basic TIA configuration with a pair of resistor RBB. So, this is a very basic TIA. It suffers from a fundamental trade offs. So, because we are interested to provide the low impedance, and that it has a many trade off, because we are also going to provide the filtering and the power consumption requirement. So, all trade offs we need to consider while designing the TIA. So, the mixer overall gain and TI input impedance are both determined by RBB. So, here this this is a GM cell, GM into V in, this is a RF GM cell, and this is a load resistance RL. So, we can write the RL divided by RL plus, it is also seeing the impedance 2 by pi square RBB, and again it is multiplied with the root 2 by pi into RBB. So, this is a mixer total conversion gain which we can represent. So, this is 2 by pi square into RBB, and this mixer is adding the conversion gain of root 2 by pi, and that will be that we are seeing at input side, we will get this root 2 by pi. At RBB, this is the impedance, and all will be multiplied with the current, that is a GM into V in. So, and this voltage is nothing but the RL divided by this RL plus 2 by pi square into RBB. So, this is we can consider it as a ZPP. So, this is a total mixer conversion gain. So, while designing the TIA, we can ensure improving the conversion gain by making RBB. So, there is a trade off, we can have a RBB which is not affecting the linearity and the noise, and also reducing the conversion gain. So, TIA configuration, the designing of TIA is important in this passive mixer design. So, if we want to overcome this trade off, so the basic two configuration of the TIA we can use is a common gate amplifier and op amp in a feedback configuration. So, two alternatives are used. So, what will happen, this both choices offer an input resistance approximately 1 by GMBB, and where GMBB is the input device transconductance. So, the large input capacitance keeps TI input impedance low. So, if you have a large input capacitance, then TI input impedance will be low at the blocker offset frequency. So, this is one of the configuration which is a common gate. We can use a common gate configuration or op amp in a feedback configuration. So, in this, if the capacitance this capacitance keeps TI input impedance very low at the blocker offset frequency. So, there are many other configuration also you can think of designing in the uh, while designing this passive mixer based receiver. You can also have your own design of TIA which will satisfy this trade off, and also have a filtering characteristics which will help to block the blockers, as well as it can use to down convert the incoming signal at the desired frequency. So, gain independence and linearity. So, the gain is now set independently by the load or a feedback resistors RF in the op amp configuration, and then we can write is GM, which is RL by RL 2 by pi square into GM BB root T root 2 by pi into RF. So, gain and input impedance can be adjusted independently. So, this is what is important, that how because input impedance of TIA will effect at the RF input side before the switch, that we already have seen that how the passive mixer is up converting the baseband impedance to the RF frequency, and it also affect the gain. So, if we can able to design a configuration which can differentiate the load input impedance and the gain. So, this feedback capacitor sets TIA bandwidth acting as a single pole RC filter. So, this is this RC filter will be up converted at the RF frequency. So, this is how we can design a TIA by using a either common gate configuration or the op amp based topology to reduce the input impedance and improve the gain. So, if we want to compare the common gate and op amp configuration, the common gate structures tends to be a smaller, since it requires a 4 times less differential load capacitance for the same bandwidth. So, if we have a let us say common gate configuration is better. Now, op amp based design may offer a superior linearity. So, on one side common gate configuration is advantageous, on other side op amp based design may offer a superior linearity. So, common gate structure may introduce a noise from the current source, which can be replaced with a resistor and large device to mitigate the flicker noise. So, that is why common gate structure will have a noise implication also, and op amp choice can be a 2 stage or complement single stage structure. However, op amp must have a sufficient bandwidth to ensure the good linearity for all blocker frequency. So, in terms of linearity, if we see, the op amp configuration is much advantageous compared to the common gate configuration. However, the common gate configuration is have a noise advantage in terms of the noise. So, we can design any of this configuration and make our receiver. For linear, mostly in the literature there is a op amp based TIA has been widely used by considering this wider bandwidth and a good linearity. Thank you. We will discuss more about this passive mixer in the next class.